Sender and I will be tag teaming this presentation as we did at Rideshare for some of you that might have been to Rideshare conference this summer. I'll go through some of the items that I talked about last year at this forum, which is really kind of the basis for the orbital maneuvering vehicle that is the centerpiece of our presentation. As I mentioned yesterday in our talk, in my brief discussion about MOOG, we now have brought together the pieces for a delivery system for CubeSats, and we're anxious to get going on it. If it's not for the lunar cubes, it's going to be for some group of cubes going somewhere, or other satellites. But CubeSats are kind of special to both Marissa and I and a number of us working at MOOG. So oh, I got it. All right. Whoop, I went one too far. Okay. I'm going to talk about the adapters that we've built, starting with ESPA and some other accommodations that go with ESPA. And then a little bit on SoftRide, which is our vibration isolation system for protecting satellites during launch. And then I'll pass the mic over to Marissa, who will talk about our orbital maneuvering vehicles built around the ESPA and potentially around some of our other adapters. So the ESPA was designed to be a secondary payload adapter for Delta IV and Atlas V. It's flown on both of those vehicles, and now it's also flown on Falcon 9 as of July of this year. But it's extended its capability beyond what its original design purpose, which was a secondary payload adapter. It's now being used by a number of organizations in addition to MOOG to provide what we call a flying ESPA, or an orbital maneuvering vehicle, or that can be called other things, but it's a modular enough system that it can carry payloads and become a upper stage of a rocket or a delivery system. It's really not part of the rocket because it's brought in by a third party, but we've worked with ULA and SpaceX to make sure that we're compatible with not just the mechanical interfaces, but the everything else involved with launching payloads. The ESPA Grande is our stretch version of our ESPA, and it's had its first launch in July of this year on the Orbcom Generation 2 launch. It's actually a stack of 2 ESPA rings that launched 6 satellites, and we're currently preparing a stack of 3 ESPA Grande rings with 11 satellites for the second part of that constellation deployment, which will occur sometime in 2015. It's not nailed down yet. But during that integration process, we got to work with the folks at SpaceX down at Slick 40 at Cape Canaveral, and also the Sierra Nevada folks who built the satellites. And SpaceX is really doing things the way the new company should be doing it, by pacing. We actually were scheduled to do the integration in less than 30 days, and we did it in 22 days at the Cape. And that was quite an ambitious schedule, because these are all hydrazine-fueled satellites, and all that had to happen right there at the Cape, and then all integrated onto the stack. But it was quite successful, and the satellites were placed exactly where Orbcom wanted them, and they're currently being checked out on orbit. Another successful launch we had this year was with our CubeStack adapter. We have the wooden model of it here, a full-scale wooden model of the CubeStack adapter out in the hallway out there. This is an adapter that's made to hold 8 3Us, 8 P-pods, or 4 CSDs from Planetary Systems or NASA Ames. It's really an adapter to hold the dispensers that launch the CubeSats. Its first launch was in November of 2013 out of Wallops on the Minotaur 1 launch vehicle. We actually stacked 2 of these adapters and put an ESPA-class satellite on top of it, the STPSat-3, and that all the satellites deployed successfully. This is the one Dan Lim talked about yesterday, the Tricept integrated in 6 days down at the Wallops facility. we are working on the second generation design of this adapter to take out some additional weight and make it a more easily integrated adapter, although it wasn't too tough to integrate. If they did 28 satellites in 6 days. So, but we're still this picture here is an image of what the second generation will look like. We can get rid of the decks, and we use a bulkhead to mount the back of the dispenser, and the front end of the dispenser would just be right on this what we call the garage door. So that's another exciting program, and we're looking forward to that. There's going to be an ORS mission, which is completely a stack of these adapters, possibly 4 or 5 of them, at no primary on top, and there will be many CubeSats. That's potentially on a super stripey mission. And that leads into the NLAS adapter, which is the first generation that the CubeSat was designed after. This adapter is going to fly on ORS-4 in January out of the Kauai Missile Range, Pacific Missile Range in Kauai, on the Super Stripey launch vehicle, which is a RailSat launch vehicle, and that would set us up for this CubeSat launch sometime after that. So this is pretty exciting for NASA Ames, and Moog built the adapter for Ames and worked with them to do the qualification of that adapter. Phantom Ride is a CubeSat, not specific, but very favorable to CubeSats. We're developing this product with Tricep Corporation. Dan Lim talked about it briefly yesterday as part of his presentation, but this is what we will show how we can put it on an ESPA ring, put 16 or possibly more CubeSats, 3U CubeSats inside a single Phantom Ride on an ESPA port, and take it to the moon. Eventually, maybe we'll get more of these Phantom Rides on. We've got to work out the delta V numbers, of course, to make something that will work. But we're excited about Phantom Ride. The trick is that it always weighs the same amount, so that if a given Phantom Ride isn't ready to go because some of the satellites aren't ready, a replacement Phantom Ride could be brought in at the last minute, and coupled loads analysis wouldn't be required because it weighs the same and it has its center of gravity at the same point, and the dynamics are equivalent. So it's a well thought out concept to carry multiple satellites in one dispenser. It gets rid of the extra mass of the individual dispenser for each CubeSat, because we have the deployment mechanisms inside the dispenser and the push out mechanisms, but does not require a P-pod or a CSD for each satellite. And you got to provide the signals to get all these satellites to deploy. So we're taking advantage of our broad reach colleagues at Moog to develop a sequencer to go along with the ESPA or the CubeSat or the Phantom Ride to take care of the deployment signals. Just a couple words on Soft Ride. We continue to increase our flight heritage with Soft Ride. We've now have 34 launches under our belt on 9 different launch vehicles. There's actually 12 different vehicles shown there, but I'm lumping all the Minotaurs together and the Delta 4s together as well. But we're continuing to have good luck with that, and I'll pass the baton to Marissa now to talk about the orbital maneuvering vehicle. Oh,
I think it works. So this is what we were talking about earlier in the design challenge, and it is a concept that's easier talked about with pictures. So this orbital maneuvering vehicle, there's been kind of a few iterations of it, and also we've looked at a number of different specific missions. And a lot of people have called it in the past the propulsive ESPA. So if you hear that term, that's the exact same thing, but orbital maneuvering vehicle is a more generic term that actually we kind of expanded the capabilities, I think. So this first picture is just a fun one, but the idea is that you take an ESPA structure and then essentially fill the inside that previously has just been empty on a launch with the avionics and the propulsion tanks and actually any other payloads. And then add a solar panel. And this is just one particular concept where we're showing that you could have your orbital maneuvering vehicle that has its solar panel, and you could deploy that. And then you could also possibly have that stacked on top of another ESPA that's just a benign ESPA that doesn't have propulsion, and those could deploy off too. So you can use these concepts in multiple different rideshare scenarios. So we've been calling it the family of OMVs because there's the idea of just the ESPA being a secondary adapter, and then there's the idea of it being a spacecraft tug. This is one concept that Joe and I both worked on, and it actually ended up with 6 spacecraft on it. And then there's also things like L-Cross or Eagle, where the ESPA has become the primary spacecraft structure. So it's really scalable, and with the ports being all a familiar interface, and the light band being something that a lot of people have used, you can do multiple different things. You can drop things off at different times and have a lot of flexibility to do more than one mission. I guess I just talked through this slide, but it's very scalable. I'll show some concepts in a minute that we have more detail on, but as Joe mentioned, the ESPA, like for instance, ESPA Grande is a taller one, and you can use larger tanks. And we've looked at a couple different, we've looked at hydrazine and the green propellant. We looked at electric propulsion a little bit, but we don't mention it in this presentation. But there's just so much flexibility to do what you want, because you can have a different number of ports, and this structure has already been proven on multiple launch vehicles. Oh, and last but not least, power. You could definitely add you can do a fixed solar array, as I'll show, but there's been concepts that already have had deployable arrays as well. So I also took a look at some of the Lunar Cubes challenges to specifically think about how we could use this. For the Lunar Volatile Orbiter, this was a lot of small payloads, and I was just looking at the Word documents that are available describing the scenarios, so if I have misinterpreted, please correct me. But in a sense, these small payloads are the easiest because you can take them in a single Phantom ride and deploy them. And then for the Lunar Surface Environmental Monitor, you could have up to, and we're showing up to 180 kilograms, so you could have 290 kilogram spacecraft that go to the moon, and then you'd still be able to use your orbital maneuvering vehicle as some sort of communications hub, like I mentioned in the Lunar Impactor challenge. And then for the mini mooners, I actually have specifically looked at the L1 scenario, and you actually need a little less than 900 meters per second to get to L1. So you can actually increase the payload capability up to a couple hundred kilograms if you want to go up to L1 with multiple 3U CubeSats. So here finally is our OMV concept, and it shows the Phantom ride here. And the solar array is actually on the back side of this one. There's a free port right here that you could put another payload onto and possibly take that with you to GTO and then drop it there, and it could go off on its own mission. And you can't see the insides of this very well, unfortunately, but there's 6 60-liter tanks, like I mentioned before lunch. So we end up with a 360 kilograms of, or 360 liters of propellant space. So the idea for this is you drop off in GTO, and then the most delta V you could get with the high performance green propellant was little under 1,400 meters per second. But from the numbers we were seeing yesterday in some of the presentations, that would suggest you could use one of the weak stability boundary orbits, or you can stack multiple of these because, as Joe said, there's missions going up that have 3 or 4 ESPAs stacked on top of each other, so you could double your capability by doing it that way. in this example here actually is showing a 4-port ESPA with, I believe it's 32 inches tall. And I threw in the end here, you could have an OMV that acts as your comm relay. And we just showed a simple X-band antenna horn in this example. This is just a quick rundown because I know everyone loves numbers. And so this is with the 180 kilogram payload. You end up right around 1,000 kilograms wet mass. And sorry, like I said, I'm repeating most of what I said earlier, but if you look at some of these other concepts where you have lots of small spacecraft, you could also do one of the ESPA rings that has 6 ports and do 20 kilogram spacecraft that would all go to the moon, and then you could actually even use the OMV to drop them off sequentially in different orbits. So in this case, though, once you go down to that 100 kilograms, you increase to about a little over 1,500 meters per second of delta V. There's that breakdown. So we see this as a way to enable missions, especially that don't necessarily need propulsive capability once they're at the moon. If you just need a ride, this is particularly a good way to go because the OMV keeps all that capability, and then your spacecraft, you can use all of your mass for the rest of your either science payload, or a lot of times it sounds like communications is a large consideration. So this can simplify the design on the small spacecraft side of things, and also just add more opportunities for what you maybe could do once you get to the moon. And I think, oh yeah, last but not least, we had a few backup slides, but the one that's probably the best just to mention here is that there is a lot of components on this OMV design that were used on the LADI mission, mode components, and we'd be leveraging that for this. Oh yeah, and one last one on Phantom Ride. So that's it.
Thank you. I have a question. Oh, unless somebody else does. What are you thinking about for comm capability? How much bandwidth? And I assume you're talking about keeping the OVM frame basically potentially in place at the target where the CubeSats are finally dispensed, so you could act as a communication node. What kind of bandwidth are you talking about?
We were looking at there's a General Dynamics small deep space transponder that's X-band. I don't know off the top of my head. I want to say 20 megabits per second, but I don't know off the top of my head what the rate is. Mm-hmm. But there's that. There's also a Space Micro one that's S-band. So they're all in the range of a couple kilograms, and either use an antenna horn like the one shown there, or like a medium gain antenna with multiple kind of feeds. I don't know.
Can you potentially have a high gain antenna?
You can really, whatever fits within the mass budget, we can do, because the OMV has lots of room to grow. If you end up looking at the ESPA spec, it's 32 inches out from the port. So you really have all that room out from the ESPA to work with. Mm-hmm. And you could actually put your antenna out on
You could stow it and then deploy it.
Yeah,
right.
So
great, thank you.
So the answer about the SDST is we use a lot of them, and we don't usually think of high rates because we're usually in deep space. It's the standard problem, but they get into the hundreds of kilobits per second, so it's a standard thing.
I'm just thinking about supporting a number of different CubeSats, so you might have some
so
demand.
it's not optimized for that.
Yeah.
Right. Yeah, so the standard goes up into the megabits per second, and things can be built to support that, but that's not what's on the shelf.
Mm-hmm.
Right.
Thanks.
So you guys have any, sorry, you actually actively talking to customers on these concepts?
yeah, there are multiple things in the works right now, but nothing that we're publicly advertising, I think is the way to put it. Would you agree with that statement, Joe?
Mm-hmm.
So, yeah, and some of the more advanced design work that actually has led to the more accurate mass budget that I showed here is what's fueling the design efforts. So it's changing from something that we just discussed and looked at internally because we want to look across MOG and see all the different ways that we can work together into something where it makes sense to come to us because we have all these capabilities rather than someone who would go out and procure all these things from us.
Excellent. Thank you very much.